Vishnu currently studying in Sri Venkateswara College of Engineering, branch CSE CY. Today I am going to talk about the topic direct memory access. So, first let us come to the introduction to direct memory access. Direct memory access is a feature that allows peripheral to access memory without involving the CPU. DMA helps improve system performance by reducing the load on the CPU. It is commonly used in devices such as hard drives, network cards, and sound cards. How DMA works? DMA transfers data directly between peripherals and memory without CPU intervention. The DMA controller coordinates the data transfer by requesting control of the system bus. This allows the CPU to continue executing other tasks while data is being transferred. Benefits of DMA: faster data transfer speeds compared to CPU managed transfers, reduced CPU utilization freeing up the CPU for other tasks, improved overall system performance and efficiency. Types of DMA transfers: single transfer involves a one time data transfer from a peripheral to memory or vice versa. Block transfer involves transferring a block of data between peripheral and memory. Burst transfer involves transferring a continuous stream of data without interruption. DMA controller. The DMA controller is a specialized hardware component responsible for managing DMA transfers. It can support multiple channels for handling simultaneous data transfers. The controller is programmed with the source and destination of data transfers. Programming in DMA. DMA transfers are typically programmed by setting up the DMA controller registers. Programmed input output PIO mode involves the CPU initiating DMA transfers. Auto initiated mode allows the DMA controller to automatically initiate transfers without CPU interventions. DMA channels. DMA channels are separate data paths that the DMA controller can use for data transfers. Each channel can be assigned to a specific peripheral for data transfer. Multiple channels allow for concurrent data transfer between peripheral and memory. DMA in operating system. Operating systems use DMA to improve system performance and efficiency. Device drivers are often responsible for managing DMA transfer in operating systems. DMA access is controlled to prevent unauthorized access to memory. Common applications of DMA: disk input output operations. DMA is commonly used to transfer the data between storage device and memory. Networking: DMA helps facilitate data transfers between network devices and memory. Audio and video processing: DMA enables fast data transfers for multimedia applications. Challenges and consideration: DMA access must be carefully managed to prevent conflicts and ensure data integrity. DMA transfers can impact system stability if not properly configured. Security measures must be in place to prevent unauthorized access to memory via DMA. DMA and real time systems. DMA is essential for real time systems that require fast and predictable data transfers. Real time operating systems often rely on DMA for efficient data handling. DMA helps reduce latency in data transfers, critical for real time applications. DMA in embedded systems. DMA is commonly used in embedded systems for efficient data transfers. Low power embedded devices benefits from DMA by reducing CPU utilization. DMA helps improve the performance of embedded systems with limited resources. Future trends in DMA. Continued advancements in DMA technology will lead to faster and more efficient data transfer. Integration of DMA with emerging technologies such as IoT and AI will drive innovation. DMA enhancement will play a crucial role in improving overall system performance. Conclusion: direct memory access is a critical feature that enhances system performance by enabling efficient data transfer. DMA reduces CPU overhead and improves overall system efficiency. Understanding and implementing DMA effectively is essential for optimizing system performance. Now let us come to our next topic, that is flip-flops as in storage element. First let us come to the introduction. What is flip-flop? Flip-flops are fundamental building blocks in digital electronic circuits. They are used as storage elements to store binary data. Flip-flops are bistable multivibrators, meaning they have two stable states. Now types of flip-flops. The most common types of flip-flops are D flip-flop, T flip-flop, JK flip-flop, JK flip-flop and SR flip-flop. Each type has its unique functionality and applications. The choice of flip-flop type depends on the specific requirements of the circuit. D flip-flop. What is D flip-flop? The D flip-flop stores a single bit of data. It has two inputs, data input D and clock input CLK. The output of the D flip-flop changes only at the rising or falling edge of the clock signal. T flip-flop. The T flip-flop toggles its output based on the clock input. It has a single input T and a clock input CLK. The output of the T flip-flop changes state when T is high and the clock signal transitions. JK flip-flop. The JK flip-flop is a versatile flip-flop that combines the features of the SR and D flip-flop. It has two inputs, J set and K reset, along with a clock input CLK. The JK flip-flop can operate in toggling set, reset or hold modes. SR flip-flop. The SR flip-flops have two inputs, S set and R reset, along with a clock input CLK. It can store one bit of data and has forbidden states to prevent invalid outputs. The SR flip-flop is commonly used for memory storage applications. Applications of flip-flops. Flip-flops are used in sequential logic circuits such as registers, counters, and memory units. They play